Okay, let's continue with with another example, which is sample problem 5.2. So the structure shown is constructed of a W250 times 167 roll steel beam. So this number is actually is just a code. Okay, this is just a code, so you don't need to worry to use this value. It is not a value, it's just a code to represent the content of this beam. Okay, so the question is, draw the shear and bending moment diagrams for the beam and the given loading. So the first question is you have to draw the shear force diagram and also the bending moment diagram. Okay, and B, determine normal stress in section just to the right and left of point D. So this is D. So what the question asks you to calculate the value of shear normal stress. So in which that this normal stress you have to calculate using MC over I. That is the equation. Or C over I is equal to 1 over S. So this also equal to M over S. Okay, so when you have a structure like this, you can see that this part is given 45 kilonewton force at point E. So when you have a structure like this, a peculiar structure like this, you transform this 45 kilonewton into point D, replace into point D, in which that if you transform, this will cause a moment at point D. So the moment, the value of moment at point D for this force 45 kilonewton is 45 times 0.6, which is equal to 27 kilonewton meter. So this will cause a moment into this direction because the force going downward here at point E. So this is 27 kilonewton meter. Okay, so we did this one. Okay, and then when you want to draw the SFD and also the BMD, you have to cut or you have to section the beam. You have to section the beam from point to point near the support. For example, from A to C, you have to cut at one section. Okay, so you have to cut the section into several. You have to cut the beam into several sections. So from A to C, you have to cut at one section, and then from C to D, you have to cut at one section, and from D to B, you have to cut into one section. So that at each section that you have cut, you can do the analysis to find the shear force, the internal shear force, and also the internal bending moment. So from there, you can create the diagram for both of shear force and also the bending moment. Okay, and then to solve the problem for question B, you have to apply, as I said, the equation normal stress is equal to MC over I, in which the MC over I is 1 over S, so it is M over S, because this one is 1 over S. Okay, so let's do this. So let's say we cut from A to C at this point. So at this point, this is called as point 1, and then from C to D we cut at one section, and then this is called point 2, and from D to B we cut at one section, and it's called as point 3. So because we already transformed that 45 kilonewton here to point D, so it will become a moment like this, 27 kilonewton meter. Okay, so first we find the shear force. The the internal shear force from A to C. One from A to C, or at point 1 from A to C. You can write maybe at point 1, okay. So you cut somewhere from A to C, but you don't know where you cut, you don't know the distance, so we name that from A to 1, we name that as X. So this is X. You don't know the distance yet, but because this one is a uniform distribution load, so we call this as a uniform distribution load, or UDL. So it is given as 45 kilonewton over meter. So this means in every 1 meter, you have 45 kilonewton load. Okay, so for x distance, the moment occurred here is acted actually in the middle of x. So the moment to represent the UDL from here to here is 45 times the distance x, which is 45x. So from here to here is x, and then in the middle where we assume it is acting, it is x over 2, so it is half. So if we consider this direction as negative, so we get that the summation of all forces in y direction is equal to 0, and then we assume this as negative. Okay, this direction is negative, so it is equal to minus 45x minus v is equal to 0. So 45x is the value of the shear force acting for this distance. Okay, so I write here 45x is the value of the shear force acting at x distance, because in 1 meter it has 45 kilonewton, in x meter it has 45x kilonewton. Okay, so that's why you got 45x. So now you got one variable here, which this is v1, and then okay, so this is shear force or bonding moment lah. Okay, so and then at point 1, the bending moment at point 1, the bending moment is equal to, if you the summation of all moment at point 1 should also equal to 0. Okay, so the bending moment for this distance x is equal to, so if you consider this direction as positive, so this 45x will cause the bending moment counterclockwise, so it is positive. Okay, so should equal to 0, and then this is 45x times half x, because from point 1, which is here, to here is half x, which is this one. So that's why 45x times half x. And then there is a moment here which is positive as well, because the direction is counterclockwise, so you have to plus m1, which is equal to 0. Okay, so for this one, maybe I write it here, v1 is equal to minus 45x kilonewton, and for this m1 it is equal to 45x times half x is equal to, so you can cut this one is equal to 22.5 So this one is minus 22.5 x. X times x is x square kilonewton meter, because this is moment. Okay, so you got from A to C, from C to D, from C to D, C to D. You also cut at one section, which is 0.2. So so the summation of all forces in F direction, if you consider this as a negative, so the summation of all forces in Y direction should equal to 0. So for point 2, is because this is 45 kilonewton meter, and the distance from A to C, is equal to 2.4. So if you calculate 45 times 2.4, you will get 108. Okay, so it is acting in the middle. So this is why you get 108. So and then when you cut at point 2, you don't know the distance from A to 2. So from A, so okay, I write. When you cut in here at point 2, you don't know this distance. So you name it as x. So that is why you get x here. So because this one 108 is acting in the middle of the uniform distribution load. So in the middle means in the middle of 2.4. So it is here. So 2.4 divided by 2. So this is 1.2 meter from here to here, because 2.4 divided by 2. So that means for what is the distance from here, this is 0.2. So what is the distance from here to here? So here to here is, because you know from A to 2 it is x. So from here to here it is x minus 1.2. So that's why you got x minus 1.2 from here to here. So the forces, the summation of all forces in point 2 is equal to 108 kilonewton, minus, because the direction is going downward, minus the 108 minus V2, because this is V2 and this is V1. So you get V2 is equal to minus 108 kilonewton. And then the summation of all moment at point 2 is also equal to 0. And if you consider this as positive, so moment at point 2 here is equal to 108, because this is positive, times the distance, which is from here to here. And the distance is x minus 1.2. And then you plus with m2. So m2 you get equal to 108. So this is 10. So 108 times 1.2, you get 129.6, and then minus 108x. Okay, kilonewton m. So this one you times with x, and this one also you times with 1.2. So you will get this value. Okay. And now at point 3, from D to B, at point 3, same, you don't know at point 3 the distance, where have you do the section, or where have you cut it. So you name from A to 3, from A to point 3, you name it as X because you don't know. So still, so that's why you got X here, because okay, and then still it is in the middle from A to C. It is acting in the middle of this 45 kilonewton, which is here. So this is 1.2 from here to here, 1.2 meter, because from A to C is 2.4. So from A into the middle is 1.2. So from here to here, is 1.2. So what is the distance from here to here? So the distance from here to here, because you know this is X, so this distance is actually X minus 1.2. So that is why you get X minus 1.2 here. We need the distance because we need to calculate the moment. That is why. Okay, so the summation of all forces in X in Y direction, so this is for point 3, yeah, which is from D to B. D to B is equal to 0. So if you consider this as a negative direction, so it is equal to minus 108, and then minus 45 kilonewton at point D, minus 45 kilonewton at point D, and minus V3, which is equal to 0. So V3 you get 153 kilonewton. And for the summation of all moment at point D3, if you consider this as positive, it's also equal to 0. So the moment is equal to 108 because it is acting here to this direction, times, so the distance is X minus 1.2, and then because you have a moment here 27 kilonewton meter, but the direction is clockwise because it is negative, so it is negative 27. And then you have one more forces here which will cause also moment, which is going downward, so it is positive because it will go to this direction. Okay, so plus 45 times with the distance from here to here, which is X minus 3.3. X minus 3.3. Okay, I will show you why this is X minus 3.3. So if you cut here, which is from A to 3 is X, okay, from A to 3 is X. So you cut, let's say you cut it here, from here to here, so it is X, okay, and then there is a load or this is a load here for 45 kilonewton, but the distance is from here, from A to D, is 2.4 plus 0.9, so it is equal to 3.3. So from here to here is 3.3. So what is the distance from here to here? So that means this one is X, this one is 3.3, so you get X minus 3.3. So that's why you got here is X minus 3.3, because from here to here, it is 3.3. Okay. Okay, so you get, and then you plus with M3, which is equal to 0. So M3, you get, you times this, you times this, and then you times this, you times this, and you solve the problem, you get 305.1 minus 153 x kilo Newton. Okay. Okay, therefore, V1 is equal to minus 45x kilonewton. Okay, at x equal to 0, V1 is equal to minus 45 times 0, so you get 0. At x equal to 2.4 a meter, you got V1 times minus 45 times 2.4, and then you get minus 108 kilonewton. For V2 or C to D, from V2 is equal to minus 108 kilonewton. So at x equal to 2.4, you get still V2 equal to minus 108 kilonewton. So, and then from D to B, V3 is equal to minus 153 kilonewton. So x equal to 3.3, V3 is minus 153 kilonewton. So if you have all this, you already have all this value, and then you can construct the shear force diagram.